our next speaker. I've had the privilege and pleasure of stalking her online for a few years now. I've seen her developing her skills as a developer, as a Redis user, as a Redis advocate. She took it upon herself. And today I'd like to present to you Elena, who came all the way from Portugal to talk to us about Redis and what happens when it runs out of memory. Thank you, Elena.
Thank you. Thank you for the nice introduction. And let me use this opportunity of being the girl with the mic to say thank you for everything you're doing for this community. And to me, you're like the perfect example of what a technology evangelist should be like. Thank you, Tamar. Applause. Thank you. Hello, everyone. While the first two presentations were talking about how Redis is being used now in the latest years and is going to be used in the future, my presentation is going to go back in time and talk about the evolution of Redis in one of its most basic use cases, Redis used as a cache. But not just that. We're going to talk about the processes that go on in an engineer's head, more specifically in Salvatore's head as he was developing the technology we all love and use. So Redis was released in 2009, March 2009, and people already started fell in love with its speed, and it already had different data structures. It didn't have any specific cache features, but people already started using it as a cache. How they did it, there weren't any memory limitations, but RAM is obviously limited. So what people did was mostly they tried to match the rate of data going in the system and coming out the system. Going in the system, obviously, bytes per second, bytes per minute. And how they were getting data out of the system, they had to set TTLs on every key to try and match the speed of data going in the system expire, so they would keep some constant memory that they were desiring. Salvatore recognized that problem, and in just 2 months or 3 months after the first release, he introduced the max memory policy. With this, now developers could set the maximum amount of memory they would like to assign to Redis to use, and what happens when we fill up that memory. So in the beginning, there was only one simple behavior. Sample 3 random volatile keys and expire the one with the shortest time to live. If there weren't any keys to expire, then an error was returned. And that was the default policy. At the time, it was the only behavior, but later it would become known as the volatile TTL. And that was the first eviction policy implemented in Redis. So, but there was a problem. He was bothered. Why do we have to delete objects if there is no need? So why are we doing this, expiring data, if maybe we're expiring data that we actually need? And why do we have to use more memory to assign to every key time to live just so we can expire it? That there must be a better way. And users started requesting some different eviction policies. So in 2010, LRU was implemented, least recently used algorithm, which was already known in cache theory. So what that did was basically, it's an assumption that says, okay, if we've used the key recently, the chance that we're going to use it again soon is quite big. If we haven't used it in a long time, we're probably not going to be using it soon or maybe even ever. Now, in order to track that, how are we tracking that? Well, we need to track when was the last time the key was used, right? So we need to track time in some way. One problem. The other problem, well, Redis is a flat key space. How are we going to select the key that we want to expire? So we're already talking about Redis internals here. How to solve some problems. The first one was maybe not that complicated because at that time, virtual memory was still being worked on. So the LRU field was already there. There was an LRU algorithm. counter, sorry. And Salvatore found 22 bits of memory to store the timestamp. But that's not enough to store the full timestamp. So what he did was a trick. He, instead of counting since the zero epoch, 1970, in the 30, 40 years in the past, he started counting from the server start time. Super simple, and I think this is the kind of thing that I love about Redis. Makes me love it because it's such a technology that's trying to optimize really for efficiency. So that was solved in 22 bits. At that time, after 2 more were added, and then we increased the clock resolution to 1 second. And the other problem, how to select the key with the longest idle time. He was presented with a problem. Am I going to change the base of my system to implement one eviction algorithm, or are we going to go with some trick? What do you think was the answer? Enjoy this quote from Salvatore. So he said, if LRU is an approximation in itself, we're not able to predict the future perfectly. With this, we're just trying to guess what is the future going to be. Well, is that worth it for us to try and implement a perfect LRU if LRU itself is an approximation? He didn't think so. I don't think so. I also think that you would think that. So he went with a simple trick. He sampled 3 random keys from the whole space and evicted the one with the highest idle time. These 3 were actually converted later in a configurable variable, so they can be configurable. You can, usually it's 5 to maybe 10, depends on what you want from your system. He implemented 2 versions of this command. One was looking for the best key to evict among all keys LRU, and the other only among the keys that are set to expire, that have a TTL. Now, 2 other eviction policies were implemented in that same round of work. Volatile random, all keys random. So depending on the pattern of access, how are you using your keys? How are you using your database? Maybe the LRU doesn't work for you. So LRU works if you have power law access. If 20% of the keys are accessed the most in 90% of the time. Okay? So in those kind of cases, LFU makes sense. But what if you have completely random access, like uniform distribution of access? Then you don't need to spend extra 22 or later 24 bits for every key just in order to use that policy. You don't need that. So if you want to be perfectly optimal, you can use volatile random or all keys random, where you just go and sample 3 random keys, and when you just randomly evict keys either from all keys or just from volatile keys. When this was released, there was no eviction included, but I think later in just 1 month or something that was already caught, there were people who weren't using Redis as a cache, wanted to use max memory, but didn't want to evict anything. It was a database, so the no eviction policy was added. Then for a while, everything went gliding along. And in March 2014, it was the time has come for the LRU algorithm to receive some attention again. Salvatore was thinking, why are we trashing so much interesting data? So if we're only sampling 3 keys, the probability that all 3 of them are actually quite good is actually quite high also. But the more we increase the max memory samples, the slower everything will get. So is there a better way? Enjoy another quote from Salvatore Sanfilippo. Observe your algorithm with naked eyes. So what he did was he created a tool, the LRU test tool. It's still in the distribution in the utils folder. You can find it and play with it a little bit. It's just Ruby script. I don't know if I have, maybe I will try to explain it a little bit. He just filled up a server, filled up completely with keys. Then he successively accessed all of them. And then he tried to push in half of those keys. That would be in theoretical LRU. That would expire the first half of the keys. And that's it. So the top graph here is the theoretical LRU. I don't know if you can see in the back, but this latest strip here is green. So maybe that's not really visible in the back. You have 3 strips. With Redis 2.8, with 5 samples, this is the result we were getting. So we were evicting keys that were in the second half of accessed keys, and we were even evicting keys from the newly added keys. It's still okay. It works. It's better than random in some cases, but it definitely can be improved. So he did a trick. Instead of evicting one of the 3 keys, he created a pool of keys where he would be storing all the best candidates. So every cycle, we sample 3 keys, we compare them to the 15 keys in the pool. If they're better, they switch place. The new keys go to the pool, the others come out. And then in the end, we evict the best candidate from that pool. That little trick improved the algorithm very much. So also with 5 samples, now we got something like this. And with 10 samples, we were getting closer to the theoretical LRU algorithm. In that same round, the LRU field, as I mentioned before, was changed to 24 bits, so we got some better resolution for the LRU expiration, now to 1 second instead of 10 seconds. The default policy changed to no eviction, which kind of made sense, because new users who just install Redis and don't know about eviction policy suddenly start seeing that their data going away and they don't know what's happening. And max memory samples default was changed to 5, and that was released in version 3.0. And then after a while, in June 2015, this issue came in. There was the developer from Hamburg who was saying that the eviction didn't work as it should, and there were keys that with TTL of 2 years that are getting evicted. The problem turned out to be eviction, cross-database eviction. So how the algorithm was working at this time, every time it went to evict a key, it went to one database, then the other, then the other, then the other. So the eviction was happening only in one database. Just a reminder, Redis can have many databases. I don't know what's the level of the audience, so let me state the obvious. So after a while, a fix was introduced for cross-database eviction. So now Redis would look at the whole database. But then while he was working on that, he said, OK, this can still be improved. Another quote from another quote from Salvatore Sanfilippo. Least frequently used eviction policy. This was already a policy that existed out there. It was talked about a lot, famous in the computer science world. And what it says basically is, well, less recently used doesn't necessarily mean that it's a more important key. Maybe we should look at the frequency of usage, the usage over time. So practically, you're getting, now you have 2 parameters to look at. You have number of access over time. And by some logic, when you have more data to make decisions, usually your decisions turn out to be a little bit more precise. So now we had 2 questions. How are we going to track the access, the number of accesses, and track the time so we can know how to decay the counter? First question, how are we going to track the counter? So we reuse the same space that we had for the LRU. So that means we have 24 bits to track the accesses and somehow store the timestamp. 16 bits were assigned to for the timer, 8 bits for the counter. And you would say, 8 bits for a counter, what's that? 255, right? From 0 to 255. That would obviously overflow. So that wasn't then an option at all. This got messed up a little bit in the slide conversion, but okay, we'll figure it out. You have companies that would consider a high number of access 1,000 hits. Other companies would consider a really high number of access 10 million hits maybe, okay? And we need a way to account for both of those or all of those use case scenarios. So we needed a way to get the scale of the company and translate that to our counter of 8 bits from 0 to 255. And that was done with a logarithmic counter. I cannot go into details because I have only like 4 minutes left, but it basically means I can actually say how we use it. Let's say you're a company, and in your company, you would consider a key important, and you wouldn't want to evict it if it gets up to 100,000 hits. So 100,000 hits would be your like maximum points. Well, then you would use the LFU log factor of 10 and use this table more or less. And that would mean that our scale now is from here to here, from 0 to 255 for 100K hits. If you consider 1,000 hits to be a very important key, then you would use this scale from 0 to 255, logarithmic factor of 0, and that would be your scale. Then that key would, 1,000 hits would probably increment the counter up to 255. And that's how, in only 8 bits, we're able to store this information of 10 million hits or more. Now, how are we going to, since we are looking at this information over time, we need to, in a while, if the key is not getting accessed, we need a way to decrease the counter, right? So for that, we need to store the last access time. 16 bits is less than we had for 24 bits for LRU. So he also used the same trick he did with the epoch starting from when the server started. But now the resolution is in minutes. So that's how we would store the last access time in minutes in these 16 bits. And every time the key is scanned, if it hasn't been accessed, the counter is halved. If it's a very low value, the counter would be decreased. Now, what happens with new keys that get added to the database, and they theoretically would have a counter of 0? They would get expired immediately, right? So that's why that problem was solved by giving a start value of 5 of the counter. This counter of, he would give a start value of 5 to all keys, so that can get a chance to get more hits. And the last thing I would like to say here, and one thing to consider, is if you're switching between LRU and LFU, you would need to be careful, because then this would mean something completely else in LRU, and for a while you would actually just end up with completely random eviction until the counters get their new values. So with all this being said, I would like to thank you, first of all, Salvatore Snafilippo, for giving us Redis. Thank you very much. And just say that I got all of this information mostly out of comments and code comments and GitHub comments and blog posts. So I would like to stress the value of making things readable, writing code, and doing our work, knowing that there will be other people looking at our work and making the work of other people a little bit easier. This is what I call empathy in code. Thank you very much.
Wow. Thank you, Elena. I asked Elena to step out of her comfort zone to prepare this presentation and to really dig in. I think she took me literally and did a wonderful effort. I loved it. Thank you. Anyone wants coffee or toilets? We're having a short break. Please feel free to step outside and refresh yourselves. We'll be back in 10 or 15 minutes, and we have a full agenda.